Section 9.2. We're dealing with hypothesis testing in this chapter, Chapter 9. In Section 1, we looked at what is hypothesis testing and talked about the basic vocabulary. Some of the how do we set this up, what is this meaning. In the next couple sections, we're getting into the nitty-gritty, how do we actually do this. So in this section, we're going to look at the critical value approach. So we're going to start with a problem, and here it is. Kevin and Diego are talking. Kevin says, hey, my average drive is 275 yards. And Diego says, yeah, right, in your dreams. Okay, so prove it. So Kevin goes and hits 25 drives. Here's the data we get from Kevin gets when he does these 25 drives. As we crunch through this data from this sample, we will get the sample mean of 264.4 yards. Not 275. Kevin still says, hey, on average, my average drive is 275 yards. And this is within reasonably close to 275. Now we looked on our confidence intervals, and they could spread out quite a bit, and it could fall within there. So this is still, my mean drive is 275. There's other things. Chance gets involved in here, right? Right? Okay. How do we decide this? And this is where hypothesis testing comes in. So we are going to do this with a critical value approach. So we start off again, how close is close enough? Because we said we can't prove it. We're going to, when we're looking at in section 1, we said at the 95%, we're looking at it now in terms of the significance level, which is that type 1 error. That 5% significance error level says we can accept at most 5% is the probability of making a type 1 error, which is the hypothesis is true, but we rejected the null hypothesis in favor of the alternate hypothesis. So we want to say, does the data provide sufficient evidence to conclude that the mean driving distance is less than 275 yards? So first thing is first, we got to set up our null and our alternate hypothesis. So our null hypothesis is going to be mu equals 275. We're a one mean hypothesis test, which means my null hypothesis will always be mu equals a number. My alternate hypothesis is going to be mu is less than 275. That's what Diego suspects. And that's what we're trying to say. Is there enough evidence? So the idea with this is there enough evidence to support Diego's suspicion to say that it's not close enough, the sample mean is not close enough to 275 to in order to not support this alternative? If it's not close enough, is it far enough so that we can support this idea that mu is less than 275 yards? So the idea with the critical value approach is we pick a cutoff value. We say, okay, how close is close enough? And we say, here, my cutoff value, this is as close as it needs to be to say, hey, we're not going to reject the null hypothesis. Or to say, hey, here's the cutoff point. If it's this or further away, then we got to say, no, we're going to reject the null hypothesis. So we're going to assume that the distances are normally distributed. It's not a large sample, it's only 25. We're not up to that 30 number, our magic number. But we can say if you sit there and driving a golf ball in the same situation, you will be normally distributed. So, and we're going to say the population standard deviation is 20 yards. Again, we're going to be working with the fact we know the population standard deviation now. We'll talk about this a little later about what if we don't know that. So since we're assuming normal distribution and we're assuming we know the standard population standard distribution, we can set up and find my mu sub x bar and my sigma sub x bar. So mu sub x bar is 275. Sigma sub x bar is sigma over the square root of n. So 20 over the square root of 25 is going to give me 4 yards. And for a test statistic, we are going to use the z-score. Since we're saying it's normally distributed, we'll go to the standard normal distribution. So we do our x bar minus mu sub x bar over sigma sub x bar, or our test statistic we'll do by taking z equals x bar minus 275 over 4. Now, to determine what my cutoff value is, I'm going to go to that 5% significant level. So again, we have a 5% chance of a type 1 error, or my alpha of 0.05. We're doing a left-tailed test, so we want the left tail, the area of the left tail, to be 0.05. That's our cutoff value. So we look that up on our table, and a z-score of negative 1.645 will give you an area of, or a probability of 0.05. So that's our cutoff score. If the test statistic is less than negative 1.64, if it's over here in the rejection where we're going to reject it, it's in that 5%, that would be the error. If it's over here on the right, we're not going to reject it. It's close enough. So we plug our 264.4 into the equation for a test statistic, and that's a negative 2.65. So we're negative 2.65 standard deviations away from the mean, which is much farther away than the negative 1.645 that we can accept. So we are going to reject the null hypothesis in favor of the alternative hypothesis. Or we're going to say, no, I believe that your mean driving range or distance is less than 275. You notice, I'm not saying that I say no, the 264 is the mean. We just say it's less than 275. Nothing more than that. We're just saying it's less than that. How much less? That's to be determined. So that's kind of a critical value hypothesis test. So we need to set up, when we're doing this, a rejection region. So this is if the test statistic runs up in the rejection region, we reject the null hypothesis. Non-rejection, if it's in this region, we don't reject null hypothesis. The critical value or values are going to be, those boundaries where we're going to separate rejection from non-rejection. So again, we have our 3 tests, our two-tailed, our left-tailed, and our right-tailed. So pretty much, two-tailed, we're going to have 2 rejection regions, because we have 2 tails. If it's in the tail, it's in the rejection region. So if we're doing a two-tailed test, we need 2 of these critical values. If it's a one-tailed test, we only need 1. Left-tailed, we're less than, so we'll find that data. That's like the one we did with Kevin and Diego. Right-tailed, we're going to be greater than that. So you need to be thinking about, am I left-tailed, am I right-tailed, am I less than, or am I greater than? When I'm comparing my test statistic to my critical value, I have to think what kind of a value, what kind of a test am I doing? So the nice thing is these critical values are based on the significance level, and if we're using common significance levels, these are pretty much already defined for us. We can find these pretty easily. So if we're doing a two-tailed test at a 5% significance level, we have to split that 5% among the 2 tails. So we take that in half, and it's 0.025, and we look that up. We would get 1.96 is going to be my z-score, so my critical values are plus or minus 1.96. If we're left tail, we just did that. We don't split it in half. We use the 0.05. We get the 1.645, and that critical value is the negative because we need to be, it's on the left, so it's going to be in the negative area. If it's a right-tailed, we're going to be a positive 1.645. So these are kind of similar to what we were doing with the normal distribution. We're just kind of seeing, why were those things important for us to look at when we're looking at the normal distribution. So as we do one of these, to do a z-test for the population, a one population mean, we need to have, we're assuming we have a normal population or a large enough sample that we can say that the sample mean is normally distributed. And we have to have sigma is known. But now you're going to state the null and the alternate hypothesis. Then you're going to find the critical values using the significance of alpha. So basically tell what kind of a test am I doing that's going to affect what these critical values are. Your test statistic is always going to be the z-score. So x bar minus mu sub 0, because mu sub x bar is mu sub 0, right? And here's your sigma divided by the square root of n. Then you're going to compare your test statistic to your critical value so you can state your conclusion. Again, your conclusion is never, I'm accepting. Your conclusion is, I'm going to reject the null hypothesis in favor of the alternate hypothesis, or I am not going, there's not enough evidence to reject the null hypothesis. It still doesn't guarantee the null hypothesis is right. It's just that this sample does not give me enough evidence to reject it. So that's part of that interpreting the results. See what you can do with these.